So empirical formulas, lowest ratio of atoms, right? Empirical formulas can be determined from elemental analysis. We can figure out the masses of elements that are produced when we decompose a compound, or we can measure the masses of the elements when they react to form a compound. So it's an experimental thing, and we're actually going to do a lab where we find the masses that combine. So we can figure it from that. If we know the percent composition, we can use that data to find the empirical formula. So the empirical formula is the ratio of atoms or moles of atoms. It's not a ratio of masses. So we're going to go to moles again, because moles is our counting unit for atoms. So for those of you who like a set of instructions, here they are. Write the mass of each element present in the sample. So sometimes they just give you masses. That's awesome. You write them down. Sometimes they give you a percentage. Well, for a percentage, you can choose any amount you want. The easy thing is to choose 100 grams. Then the percent is the same as the mass in grams. So that's the easiest thing. So you're starting with the masses, then you have to convert those to moles using molar masses of the elements. And then your book talks about writing a pseudo formula. If you want to do that, that's fine. I've never really liked that. So I don't like that part. So in that pseudo formula, then you would divide the subscripts by the smallest subscripts. So I say, well, let's just keep it in terms of moles of each element. Divide all the moles by the smallest number of moles. We're trying to get whole number ratios of numbers of atoms. Sometimes that number comes close to a whole number, and sometimes it doesn't. And so it can be difficult for students to know when is it okay to round to a whole number and when is it not okay. If the result is within 0.2 of being a whole number, so like 1.8 or 7.85, less than 0.2 away from the closest whole number, you can round it. Otherwise, you're going to have to multiply all of those by the same number to get whole numbers. And so this comes down to, decimal equivalents of fractions. 0.2 is a fifth, so if you multiply by 5, you're going to get a whole number. 0.25 is a fourth, 0.33 is a third, etc. So that table is nice. If you recognize the decimal equivalents of fractions, you can just go directly to the correct number. My experience is a lot of students are like, what the heck did you just talk about? Okay, so here's the short one. Multiply by 2. Does that give you whole numbers? Awesome, you're done. Didn't work? Try 3. Try 4. Try 5. If you get to 5 and it's still not working, something else is probably wrong. So let's do an example. Sample of a compound is decomposed in the lab and produces 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. Calculate the empirical formula. So we're going to take the masses of each element and write them down. 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. They did an experiment and they got these numbers. So we're going to take masses and convert to moles. So to convert grams to moles, I want to multiply by mole and divide by gram. So for carbon, these are the masses on the periodic table. One mole weighs 12.01 grams. The grams cancel out. 165 divided by 12.01. 13.7. For significant figures here, more is better. Okay, so if you're not sure, write some extra ones. If you round these too much, that will affect your ultimate formula. So 165 has 3 significant figures. I'm going to keep the 3 and 2 extra digits. So that's my moles of carbon. And then I'm going to convert hydrogen to moles, 1.008 grams. So 27.8 divided by 1.008. It's tempting to just ignore that 8 at the end there, but don't do it. 27.579 moles of hydrogen. And then 220.2 grams of oxygen. 1 mole of oxygen is 16 grams. 220.2 divided by 16. 13.762. There's only one more digit. I might as well just write that one down too. So we could make a pseudo formula, a fake formula, C 13.738, H 27.578, O 13.7625. But why? We need to make these into whole numbers. We cannot just round them to whole numbers and call it good. We need a ratio. So the ratios, we want to get whole numbers. So what we do is we take the smallest one, we divide all of them by the smallest. That way, the smallest ratio we're going to get is 1, and everything else will be larger than 1. So we look at these, and 13.738 is actually the smallest, right? It's a tiny bit smaller than this one. So I'm going to divide this one by itself, and that's going to give me exactly 1. And I'm going to divide this one by 13.738. And I'm going to divide this one by 13.738. That was too messy. So the one on the bottom comes out to be 1.0017 and 27.579 divided by 13.738. This gives me 2.0074. So those are the ratios. You're going to get exactly 1 for one of them. When I look at 2.0074 and 1.0017, those are less than 0.2 away from the nearest whole number. So they can be rounded. So we're going to call this 2, and we're going to call this 1. They don't come out exactly perfect because this comes from experimental data and there is some error, some uncertainty. So the formula then, this is the subscript for carbon, this is the subscript for hydrogen, this is the subscript for oxygen. And since we don't write 1s in there, it's CH2O. Any questions? Yeah.
How would you know what to put them in? Like, you could have put like C or H.
Oh, the order?
Yeah,
okay. So that's an excellent question. How do you know the order? Well, usually, I mean, you could follow the rule of the more metallic element first, but then where does hydrogen play into that, et cetera? So what actually works really, really well is the problem will usually give it to you in the correct order. So just do the same order. Yeah, right?
Oh,
Yeah.
yeah.
This is the empirical formula for an organic compound, and organic chemistry has its own little particulars about order and how you write things. Any other questions? And I will not try to trick you on the order that you put these in. I'm concerned with, did you get this whole messy process? If you got that, I don't care if you wrote OH2C. It looks silly to me, but it's fine. Let's do another one. Here's ibuprofen again. It's my drug of choice for any ailment that my children have. They come in, I sprained my ankle, take some ibuprofen. I have a headache, take some ibuprofen. Why not aspirin? Ibuprofen's safer. And I could tell you a story about Tylenol and ibuprofen, but we'll do that off the record. And it involved poison control in the emergency room. Okay, here's the percent composition. What's the empirical formula? So they didn't give us masses. What we want to do is say, well, let's assume we have 100 grams. The empirical formula is going to be the same, no matter how much stuff we have. The percent composition is the same. So we choose things to make it easier on ourselves. 75.69% means 75.69 grams out of 100 grams. So let's say we have 100 grams. And then we just write down those numbers, and we put gram instead of percent. So we've got 75.69 grams of carbon. And we've got 8.80 grams of hydrogen. And we have 15.51 grams of oxygen. We're going to convert these to moles. It's the remembering what steps to do that's the hard part. The individual pieces really aren't that bad. It's just remembering, what am I supposed to do next? So go to moles. 1 mole over 12.01 grams. It'd be so much easier if I just played the video from yesterday and I could just sit down, but I'm going to do it over again. 6.302. I'm really only paying attention to significant figures here just to make sure that I keep enough of them. Bless you. You can tell the air quality is bad when everybody's sneezing. So this gives me 8.7301 moles of hydrogen. That's carbon. And 1 mole over 16. So that's going to be close to 1, but not quite 1. 0.9693. 0.969375 moles of oxygen. So we figure out the moles of each element, and then we need the ratio. So we take the smallest number of moles and we divide everything by the smallest. So this time this is the smallest. So that one ends up being 1. That's nice. Then we've got this one divided by 0.969375. $9.0059. And then 6.30224 divided by 0.969375 equals 6.5013. Nice whole number. We can round that to a whole number. 6.5. Can we round that?
Would you times it?
We need to multiply it. We need to get whole numbers. So if I multiply this by 2, so that number times 2 in my calculator, 13.0026. That's close enough, I can round to 13. If I multiply the first one by 2, I have to multiply all the rest of them by 2 in order to keep the ratio the same. So I multiply this one by 2. It's going to end up rounding to 18, but let's just be thorough here. 18.011. Okay, so that can be rounded to 18. And then I have 1 times 2 is 2. So I have a ratio of 13 to 18 to 2. That is the same ratio as 6.5 to 9 to 1. But I have to have it in whole numbers because I can't have 6.5 atoms of carbon. So I've got C13, H18, O2. That is the empirical formula for ibuprofen. Yes?
Sorry, I spaced a little bit. Why did you multiply the other two numbers by 2?
Because I need to keep, I multiplied all of them by 2 because I need to keep the ratio the same. If I didn't multiply both of them, then it wouldn't be the same anymore. So, quick illustration of that. If I have a ratio that's 1 to 3, and I multiply the bottom by 2, that's going to give me 6. If I don't do anything to the top, is the ratio 1 to 6 the same as 1 to 3? No, I have to multiply the top also, and 2 to 6 is the same as 1 to 3. Okay. Any other questions? So the empirical formula comes from the experimental data. How do we get the molecular formula? Are we going to take a break? We're going to have a nice long break before the exam. We're almost there. Almost there. Just hang in there. The molecular formula is some multiple of the empirical formula. It could be the same, in which case it's multiplied by 1, right? Or it could be twice as big or 3 times as big. So to find the molecular formula, we need the molar mass of the compound, and that would have to be given to you. Okay? There's nothing in the problem that would allow you to calculate that. So the molecular formula is some number multiplied by the empirical formula. So we need to find out how many empirical formulas fit into the molecular formula. They give us the molar mass, and so we find the mass of the empirical formula. Take the molar mass, divide by the mass of the empirical formula. That will give us a nice whole number, and we multiply all the subscripts. Ah, shoot, there's that part too. Dang it, I forgot about that one. Okay, let's do this. We can do this. So compound has the empirical formula CH. The molar mass is 78.11. What's the molecular formula? So the molecular formula is going to be some multiple of that. So to find what N is, we take the molar mass that we're given for the entire compound, and we're going to divide by the mass of the empirical formula. So that's 12.01 plus 1.008, which is 13.018 grams per mole. I want to know how many CHs fit into the whole formula. So I'm going to find out how many masses of that fit into the actual molar mass. They are losing it over there. 13.018. 6.00015. There's no need to multiply this. If it doesn't come out to a whole number, you did something wrong. It's always going to come out to a whole number. So n equals 6. I'm taking my empirical formula and I'm multiplying all the subscripts by 6. This is just kind of a help you understand what's going on. That's not the answer. We're going to end up with C. Psst, that's not a C. C6, H6. Yeah. You could simplify that. So this is not the simplest ratio. It's not an empirical formula. This is the empirical formula, CH. This is the actual molecular formula. Yeah. So in this molecule, which happens to be benzene, there's 6 carbons and 6 hydrogens all covalently bond together, and that's a molecule. We can only get the simplest ratio when we determine it experimentally. Okay, I'm done, and I can tell that you guys are done too.